Hi, in this lecture, I'll be talking about regression analysis, which is my favorite thing to teach about, and it is a method of making predictions using existing information about something that we really want to learn about. So in today's lecture, I will just give a brief introduction to prediction or regression. We'll talk about how to draw the regression line, and then finally I'll give you brief exposure for how to calculate the components of what we call the regression line. And regression is really crucial to psychology because we are often wanting to make predictions or educated guesses based on known information. So you could consider, for example, wanting to understand how a reading program is likely to help a particular third grader. So what is their reading performance going to be like after their performance in a reading program? Or how likely do we think a particular patient is to engage in self-harming behaviors given known characteristics or experiences? Or if we know an infant's traits at a really young age that we think might be linked to autism, we might be able to predict a later diagnosis on the autism spectrum for that individual. So basically, if we know that two variables are related to one another or correlated, as you're familiar with from our previous lecture, then we should be able to predict one of those variables from the other related variable. And for predictions, you can use either z-scores or raw scores. So you could create z-scores out of your x and your y variables, and then use the z-score for x to predict the z-score on y. The benefit for doing that is that you get this variables all on the same scale. That's really beneficial for when you have multiple predictors. That's for an analysis called multiple regression. But for now, we're going to stick to simple regression, where we have a single predictor for a single outcome. And in simple regression, it's more common to just use the raw scores to predict raw scores. So just using the original x scores as they are to predict y values on the original y scale. So for example, and this is the example that we'll stick with for this lecture, we might be interested in predicting college students' level of imposter syndrome. If you haven't heard of imposter syndrome, it's really common, especially in academia, especially among students. Maybe you've experienced it yourself. It's basically a feeling where you think, I'm not good enough to be here. I'm not as smart as all of my peers. I'm not as smart as all these people around me. It must be an accident that they let me be here, and someday I'm going to be found out. And so then you work extra hard and you try to do your very best to not be found out as an imposter in your environment. And we know that self-esteem is a trait that's pretty linked to imposter syndrome. There's a lot of things that could be linked, but self-esteem is one of them. And we know specifically that people who have lower self-esteem tend to have higher rates of imposter syndrome. So we know that SE, self-esteem, is correlated with IS, imposter syndrome. So we could collect information on both of those variables. And let's say that we use a self-esteem scale where scores can range from 0 to 15, with 0 being no self-esteem and 15 being high self-esteem. And individuals' imposter syndrome scores are collected on a scale of 0 to 12, with 0 being very low imposter syndrome and 12 being really high levels of imposter syndrome. And we'll use the information that we collect from the individuals on these two scales to create what we will call a prediction rule. The prediction rule is a small formula that helps us guess the individual's outcome, in this case, imposter syndrome, based on what we know about their predictor, their self-esteem level. And when we engage in this prediction, we are doing regression. So we're predicting a variable's score from another variable's score, and that's called regression. And this equation that you see on the screen, y equals a plus bx, is the format for the prediction rule. Like I said, it's a little small formula. And in this equation, we are predicting y from x. We can also say we are regressing y on x. And you might notice that the y here in the formula looks a little funny because it has a little caret on top of it. We call that y hat. And it's different from y because this is a predicted value for y. So the predicted y score, not necessarily the observed y score, but what we predict y will be, is called y hat. This formula might also look familiar to you. If you think about it back to maybe high school math courses, it kind of looks like y equals mx plus b, right? That's the formula for a line. And that's a little hint for where we're going to go in this lecture. So to predict a person's score on y, or to predict y hat, we start with some baseline number, and we'll call that a. So we have some sort of baseline that everyone gets. And then we add to it the product of b times x. And x is their score on the predictor variable. So a and b, what are those things? A is what we call the regression constant, and b is what we call the regression coefficient. Let's get into those a little bit. The regression constant, a, is the expected or predicted score on the outcome, also sometimes called the criterion, when an individual's score on the predictor is 0. So in other words, this is the y value when x is at 0. And that should make mathematical sense to you. If you look at the equation for a second, you'll see that if x is 0 in this formula, then all we're left with is y equals a plus b times 0, or y equals a. So y will just be equal to a if x is 0. This is also sometimes called the y-intercept. A is sometimes called the y-intercept. And that's because it's where the line, the prediction line that we'll look at in a few minutes, crosses the y-axis. So this is actually a formula for a line, and A is the intercept, the y-intercept for that line. The regression coefficient, or b, is also called the slope. And that's because it is the slope of the regression line that we'll look at in a minute. And the definition of this value is the expected change in the criterion or outcome for every single unit change in the predictor. So whatever b is equal to, b is the expected change in y for a single unit change in x. And when I say single unit, I really just mean for every 1 point increase in x. So right now x is self-esteem, so b will be equal to the expected change in imposter syndrome scores for each point increase on the self-esteem scale. Okay, so now not focusing on how we would even calculate A or B, so we don't know where these values came from for now. You'll learn how to calculate them later. But for now, let's say we're just handed those values. So we know that A is equal to 10.3, and we know that B is equal to negative 0.4. Then we would plug those in to this little equation to get our prediction rule. So our specific prediction rule for our study is y hat equals 10.3 plus negative 0.4 times x. And what this tells us right away, just by looking at our prediction rule, we know that someone with a self-esteem score of 0 would be expected to have an imposter syndrome score of 10.3. Remember that imposter syndrome scores can go up to 12. So someone with no self-esteem would be likely to have really high imposter syndrome. That makes sense. And we also know that for every point increase on the self-esteem scale, so as someone's self-esteem score goes from 0 to 1, or from 1 to 2, or from 2 to 3, so as their self-esteem score is climbing, for each point that it climbs, then we expect to see their imposter syndrome score going down by 0.4 points. Okay, now for the fun part, let's talk about how to draw the regression line. First, let's draw our two axes. And we'll label those axes as we would for a scatter plot. But here, it's important that we put the x variable along the x-axis and the y variable along the y-axis. So our x variable is our predictor variable. That is self-esteem. And our y variable is our outcome variable, our predicted variable, and that is imposter syndrome. Remember that self-esteem scores can go up to 15, and I'll just put a few other points on here. And remember that imposter syndrome scores can go to 12. That's a 6 there. Okay, so to draw our regression line, after we've labeled our axes, the next step is to choose a low value of x, any low value, and then plug it into our equation. This is the fun part, to find the predicted value for y. So we get to pick any value we want. It would be really wise to choose 0 because it makes the math a little simpler. So if I plug 0 in for x into this equation, then I just get y hat equals 10.3 plus -4 times 0. And we knew that because that's the definition of our intercept or constant term. That's A. So someone with a self-esteem score of 0, so they're over here on this axis, is expected to have an imposter syndrome score of 10.3. So that's somewhere up here. Okay, so now that we have picked a low point on our predictor variable to plug into the prediction rule, now we want to pick a high value on the predictor variable to plug into the prediction rule. And let's just choose 15. So someone with the highest possible self-esteem score of 15 has an x equal to 15. So what is y if x equals 15? So now we have y hat equals 10.3 plus -0.4 times 15. If I do that math, I get a value of 4.3 for my predicted imposter syndrome score for someone with a self-esteem score of 15. So we're over here, someone with self-esteem of 15 has an expected imposter syndrome score of 4.3. So I'm going over 15 and up 4.3 points. So now I have 2 points on my plotting plane, and I know that this is a linear relationship. So I know that I can draw a straight line between these 2 points. This regression line is an indicator of the relationship between the predictor variable and the predicted variable, or the criterion variable. And as I mentioned, the slope of the regression line is equal to b, or the regression coefficient. And again, this tells us that for every single unit increase in someone's self-esteem score, then their imposter syndrome score is expected to decrease by 0.4 points. And our intercept value, or constant, is equal to A. And remember, A in our example is 10.3. And this tells us that if a student has a self-esteem score of 0, then their expected imposter syndrome score would be 10.3. So this is our prediction rule for predicting imposter syndrome from self-esteem. So how did I get those values of A and B? How do we know which formula is the best formula to use for our regression equation? We are going to use what we call the least square error principle. This is the theory behind the equations we'll use for calculating A and B. And in the least square error principle, error is defined as someone's actual score minus their predicted score. So recall that y hat is someone's predicted value on imposter syndrome. But I've also observed actual imposter syndrome scores. So I know what every single person's imposter syndrome score actually is. So if I want to know error, or how much error there is in my prediction, then I would want to observe how far off my estimate was for each individual. So how far off am I when I predict someone's imposter syndrome level? And of course, the best equation is an equation that minimizes that error. So it's the most accurate prediction rule. We want to minimize error. So the theory is that the best equation will have a regression line that fits the data better than any other possible line. Or in other words, it minimizes the distance between the actual points and the predicted points, or the points on the line. And this line that fits the data better than any other possible line, or minimizes the distance from the points on the scatter plot and the points on the line, is called the line of best fit. And here's just a visual to help you understand that. Errors here are shown in red. So we have individuals' scores shown in the blue diamonds. Those are the actual values of y. And then notice that we draw a line through those points. And the best fitting line is the line that minimizes total error. So we're going to underestimate for some individuals. Notice that our estimate right here, our estimate right here, and our estimate right here, these are underestimates for all these individuals. And then for some individuals, we have overestimated their value in this visual. So for this person here, we thought they would have a value at this point, but their actual value is where I've drawn this arrow. So we've overestimated for that individual. The best fitting line will be the line that equally over and underestimates, therefore minimizing the total amount of error. And using this principle, the least square error principle, that minimizes error, we can derive these two equations for calculating A and B. So these are the formulas that we'll use to calculate A and B that will give us the best fitting line, or the line that leads to the least error. That's the end of this lecture, but I'll upload another resource that will walk through how to plug values into these two equations to actually calculate the best fitting regression line.